For the final project of CI's 565, I was doing GPU accelerated path tracing. Path tracing is a global illumination technique that simulates light transport in real world as closely as possible. It is based on this rendering equation proposed by Kojia in 1986. To approximate this integral term here, Monte Carlo methods are used. That is, if a ray hit a diffuse surface, multiple rays will be generated in order to approximate the rendering equation. So that is why path tracing is extremely expensive. Even a simple thing like a Cornell box with two spheres would take as long as 30 minutes to render on CPU. However, based on the underlying parallelism that color computation of a certain pixel is independent from other pixels, it's absolutely possible to move the whole process of path tracing onto GPU, and the sweet result will be orders of magnitude faster. Here are three images of my GPU path tracer. This first one took around 10 seconds to render and is pretty noisy. And the second one here took around 1 minute to render and has a much better quality. The third one, which took around 150 seconds to render, you can barely see any noise here. So if I compare this one to one that is rendered on CPU, it's already around more than 10 times faster. So, however, still does not look like a real image taken by a camera. The reason is pinhole camera has no depth of field. So after I modified the camera model, the image render looked like this. In this picture, the camera focused on the icosahedrons near, so the mirror sphere far away looks somehow blurred. But if I adjust the focal perimeter for the camera to focus on the mirror sphere, the image will look like this. So what else features are available about my path tracer? Let's look at an image. In this image, if you pay close attention, there's totally no reflection on the glass sphere, which is not physically correct. In real world, when light transports from one medium to another, both reflection and refraction will happen. To make it physically correct, I added Fresnel equations, which are used to calculate the ratio between reflection and refraction. The result image looks like this. Compare this one to the first one. You can notice the difference on the glass sphere. So this one, the second one here is definitely more realistic. Also, I add jittering for anti-aliasing. The difference is trivial and hard to perceive, but if you look at the zoomed in image and compare, a slight difference could be found on the edges. The image on the right is a more jagged one because no jittering or anti-aliasing technique is used. That's pretty much everything I've done. Let's take a look at how the application works while running. After the application is launched, the frame buffer starts to accumulate image rendered per tap. And the image you see at every moment is actually an average of all previous frames. You can adjust the focal plane parameter or the aperture parameter like this to use different lengths for depth of field effect. Also, you can move your camera like this and also the viewing direction. And every time you update the camera, the frame buffer will be clear.